Okay, in this lecture we're going to cover the second part of our section 4.2 material regarding the column space of a matrix. So in the first part of this section we introduced the null space. Here we'll talk about another related subspace called the column space. Now, unlike the null space of a matrix, the column space can be defined explicitly via linear combinations of the columns of A. So let's see how it's defined here. We would say the column space of an m by n matrix A, which is denoted as col A, is the set of all linear combinations of the columns of A. So in particular, if A is the m by n matrix whose n columns are the vectors a1, a2 through an, then the column space of A is the spanning set, or the set generated by those vectors, a1 through an. Now, a typical vector in the column space of A can be written as A times X for some vector X, because the notation A times X, we know, can be used to represent a linear combination of the columns of A. So the entries in that vector X, or the weights of the linear combination in our column space. So another way we could define the column space of A is as the set of vectors B such that B is equal to A times X for some vector X in Rn. Now this notation, A times X for vectors in the column space of A, also shows that the column space of A can be thought of as the range of a linear transformation where X maps to A times X. So again, if we have our vector space Rn, and we have a linear transformation T, which is taking vectors X in Rn and mapping them to vectors A times X in Rm, then the column space of A would be the range of this linear transformation. So if we take the set of all vectors in Rn, so all of Rn, and we map those vectors under this transformation T into Rm, well, we might not hit all of Rm, but the range of that linear transformation, which would be a subset of Rm, is our column space of A. All right. Now again, the terminology that we're using here, column space, is appropriate because the column space is indeed a subspace of Rn. So here the following theorem, 4.3, gives us that result. Here, the column space of an m by n matrix A is a subspace of Rn. So let's see if we can verify that result. So here, we can say clearly the column space of an m by n matrix A is a subset of Rm, since A is an m by n matrix. So when I take a m by n matrix and multiply by an n by 1 column vector, the result is an m by 1 vector, so the column space must be a subset of Rm. And based on the definition of the column space of a matrix as the span of the vectors a1 through an, which are its columns, we know that the column space of A is a subspace by applying theorem 4.1. So we get our result directly by applying theorem 4.1 and realizing that for an m by n matrix, the elements of the column space must be in Rm. So since the column space is a spanning set for a set of vectors, then by theorem 4.1, it is itself a subspace. So let's look at some examples working with the column space. So in this first example, we are asked to find a matrix A such that the given set would be the column space of A. So here the set of vectors that we're given, let me give this set a name, maybe W, is the set of vectors in R3. So we know that A is going to have 3 rows. And it's the set of vectors of this form where A and B can be any real numbers. So here we note that we could write W, or the vectors in W, as a linear combination of 2 vectors with weights given by these constants, A and B. So for A, we would be multiplying by the vector of A coefficients, so 6, 1, negative 7, plus B times negative 1, 1, 0, where A and B could be any real numbers. So here, if we think about these 2 vectors, where vectors in W are a linear combination of these 2. Let's call them V1 and V2. The space W that we're given here is the span of these 2 vectors, V1 and V2. So we know that the column space of a matrix is defined as a spanning set for a set of vectors, which are the columns of that matrix. So for the set W, let's take, which is the spanning set of V1 and V2, let's take the matrix A to be the matrix which has V1 and V2 as its columns. So in this case, W is equal to the column space of A, because the column space is by definition the span of the vectors which form the columns of that matrix A. So here, A would be the matrix which we've found here. Now in our next example, we've got the exact same sort of problem. We're asked to find a matrix A such that the given set, again, I'll call it W, is the column space of that matrix. So again, we see that we could write W, or the vectors in W, as a linear combination of vectors whose weights are A, B, and C. So here we could have A times 1, 2, 0, 0, plus B times negative 1, 1, 5, 0, plus C times 0, 1, negative 4, 1, such that A, B, and C are real numbers. So these 3 vectors which generate the set W, let's call them V1, V2, and V3. So we see here that W is the span of that set of vectors, which could be considered as the column space of a matrix A, where A is the matrix which has these vectors as its columns. 1, 2, 0, 0, negative 1, 1, 5, 0, and 0, 1, negative 4, 1. All right. So let us recall that the columns of A will span all of Rm if and only if the equation Ax equals to b has a solution for each b. So that fact we could restate in terms of the column space of that matrix in the following way. We would say that the column space of an m by n matrix A consists of all of Rm if and only if the equation Ax equals to b has a solution for each b in Rn.